Sammen. Det noen ledige plasser her foran, og det all grunn til å bruke hver bidige sete i dette kontoret i dag. Og det litt sånn innimellom her også, så trekk fremover og se. Ja, kjære alle sammen, velkommen hit til Egget ved Universitetet i Bergen. Mitt navn Dag Rune Olsen. Jeg det som kalles dekan på Matematikfakultetet, altså matematisk-naturvitenskapelig fakultet, for dere som ikke jobber her og vet ikke hva det Men altså, det meg som har ansvaret for det som vi sysler med, som forskning og utdanning innenfor realfag, verdens viktigste områder, naturligvis. Jeg kommer til å si noen få ord, men da gjør jeg det på engelsk, fordi vi har en del engelskspråklige i salen, så jeg håper at det går greit, ikke minst fordi at foredraget også kommer til å være på engelsk etter hvert. So, welcome to you all. My name is Dag Rune Olsen. I'm a dean at the science faculty here at the University of Bergen, and it's a pleasure to see so many people that is in the audience today. This lecture is a lecture in a series of lectures called Horizons, and Horizon is looking behind, looking ahead, and that's what science is all about, isn't it? Lately, there has been some really interesting breakthroughs in one of the fields I think is of particular importance when it comes to, let's say, curiosity-driven research, and that is, of course, related to the activities at Cern. I do know that all of you are expecting to listen to and watch and perhaps even talk to later on Professor Bertolucci, Research Director at Cern. But strikes in Lufthansa did not make that possible. So you will not meet him today. But in very short notice, we have found the very, very best stand-in substitute that is possible to dig out. And that is our own Professor Anna Liebnacker. She will give Bertolucci's talk. He sent his PowerPoint presentation and has briefed Anna this night and things like that, so she is on the tiptoes to deliver his talk. So I'm sure that you will be more than satisfied. Beside that, I think it's important to realize that a topic like looking for the Higgs particle, it's not really one of the trivial scientific studies to undertake. It's highly theoretical. Of course, it's practical research down at Cern, but and that kind of research represents an abstraction level, which I think is tremendous. Yet, all the endeavors and all the recent discoveries has made it to the press. And I think that is also extremely important because it shows that it is possible to communicate also the big events and important events in curiosity-driven science. Anna Liebnacker, that you will meet later on, she wrote in the Morgenbladet together with a colleague, Heidi Sandmaker, which is also a Cern scientist, physicist, both of them, at the University of Bergen, wrote in the Morgenbladet, local Norwegian newspaper, if you can, or magazine probably rather, about these important events. And I think that is also an important thing for researchers, university staff to undertake, to try to communicate to a broad audience what it is all about. Of course, it's not everybody that is that thrilled with the Higgs particle or the events. And some are more thrilled than others. One guy said that, gosh, they found the Higgs particle and the lady over there didn't really knew it was missing. So she was not really keen on this. But I'm sure there are differences in opinion with respect to whether this is tremendously important or not. To set the stage, Professor Per Åstrand will introduce Bertolucci and say a few words about his research, even though he's not present. And then also perhaps a few words about Anna before she is given the floor and enlighten us with the recent discoveries regarding the Higgs particle. Please, Ben.
Okay, thank you very much. First, a correction, if I may, to Dr. My name is Per Osland, not Osland. In my part of Norway, there's a big difference between these two names. Well, it's more. As Dr. said, I'm a professor of physics in the Institute for Physics and Technology. And I'll say a few words about Sergio Bertolucci, who unfortunately wasn't able to come. He was born into a very systematic...
Speak in the microphone. We're getting old, some of us.
You're getting what? He was born into a very systematic family on January 1st, 1950. Can you imagine a better birth date? He got his degree at the University of Pisa. He has worked mostly at DESI, at the Fermilab, at the Frascati. At Fermilab, he was very much involved in the discovery of the top quark in 1995. He's been director of the Frascati lab for a few years. He's been on various international committees to evaluate and decide what's important in research. And presently he's director of research and scientific computing at Cern. He left Geneva at 8 o'clock last night with Lufthansa, but unfortunately that plane was late. He got to Frankfurt late, and then he got stuck on a bus for 15 minutes on the runway before they were able to get to the gate. So he lost his connection to Bergen at 9:30 last night. And then Anna generously agreed to give his talk at short 7-8 hours notice. And I will try now to connect the computer to that talk. So just a moment.
Okay, good morning everybody. I'm sorry I'm not Sergio Bertolucci. Yes, then I'll switch on the mic, yes. Okay, now it should be louder if not better. Yeah. Fine. There is some optimal distance. Is it better? Is it okay now? I'm hanging down the nasty beast. Yeah. Okay. Now it should be. So, yeah. I think I have to keep it in my hand, otherwise I don't have a collar which is long enough to be in the right position. Of course, it's a pity Sergio Bertolucci didn't make it. Well, the good part of it that man kan stille sportsmal på norsk at foredrag. Also, the other good part of it is that I have the whole Atlas and Cern team at University of Bergen, who is sitting somewhere in the audience, as Professor Bjarne Stugu, Professor Gerald Eigen, and lots of PhD students we have, so who will help me if I need help to answer your question and also during this talk. So this will be really a team effort, and the only reason I'm the stand-in is because I have this stupid habit to answering phones late in the night, and also Also because of many less and more intelligent things I was doing in my youth is being trained as a stand-in for actors in difficult situations. So that's what I'm doing today. I hope it will end well for all of us. Okay, so it's also a pleasure to have slides prepared by a Cern research director. It doesn't happen so often to a single professor in Bergen, so we're going to all enjoy it. So the title of this talk is Big Question, Small Particles, and how the curiosity-driven science leads us to big things which are useful to enlarge our minds, culture, and not only actually to apply it in a real life, affecting everybody here. So this talk will start with introducing mission of Cern. What this abbreviation mean? Actually, abbreviation means Conseil Européen de Recherche Nucléaire, which means laboratory for nuclear physics. But Cern is not anymore, strictly speaking, laboratory for nuclear physics. It's doing high energy physics, nuclear physics, medical physics as well. And essentially it sees its mission as pushing the frontier of knowledge, as educating people and developing new technologies. So the mission of training, research, development of technologies, all these missions are there in. So on these pictures you can see, for example, there is a picture from PET scanner. It's a PET and tomography, computer tomography, which uses devices at Cern. And you can see young scientists being trained. Cern has lots of training programs for students, postdoctoral researchers, students of various levels, and some people who are here in the audience were, for example, summer students at Cern. This is open for everybody, and I hope some of you will go there, get trained, meet other people, see the Cern mission. One important mission is to unite people from different countries in their common goal, doing science. So science is a universal language of mankind. So it happens. We can all understand each other on the platform of science. And Cern started as a laboratory for peace. I will speak about it a second later. But what's also important is that many discoveries which we use in everyday life started as a byproduct of basic research, curiosity-driven research of curiosity. Just to give an example, if you would like to improve candle, you would probably not invent electric bulb. This needed a new concept, something which is, and understanding nature to the level which would allow you to build this device. So without understanding how nature works on a very basic level, we are not able to progress further in building new technology for the future. So as many people say, trying to understand things now just because we don't know how they work is building technology for the future. So, Cern was founded in 1954, and actually Norway was one of the founding countries of Cern. Some people say that this is pretty accidental, that Cern is located where it is located on the border between France and Switzerland, and the only reason why it's not located in Norway is because when this idea was to be considered by Norwegian parliament. They were on vacation, so unfortunately this was in the Felles ferie, so the answer was too late. But Norway is one of the founding countries, and now there is a large number of member states. Essentially nearly all European countries are member states of Cern. Then there are some candidate countries for accession, for example, Romania, and there are observer and associate member states. So these associate member states, some of them might join, so Israel might be the first non-European country to be a full member. But then there are also applicant states and observer countries which play a big role. So it's India, Japan, Russian Federation, the United States, which play a big role in CERN research. So, as you see, CERN doesn't have such a big scientific staff. There is around 2,000 people of scientific staff and around 1,000 of other. So this is permanent staff of other paid personnel, associate staff. CERN staff is mainly concerned with development of accelerators and computing and administrative duties. But there is a very big group of CERN users, and CERN users are people like me, like other professors and students in Bergen. So CERN users actually build detectors and do, as we call, physics. They contribute to building detectors, they contribute to developing computing, they actually do the research which I'm going to present. So the research which I'm going to present is done by the huge community of around 11,000 of CERN users. And these CERN users come from a large number of countries in the world. You can see here the whole map. And in the blue there are member state countries, in green there are associate states, and in red there are other countries from which CERN users originate. So you can see that CERN users are on every continent, including Africa, although not so much, and also in Iceland. Now, there are two, I'm going to say a bit more about it later, but I wanted to say something about Norwegian contribution to the physics I'm going to talk about. So Norway is in two experimental collaboration, Atlas and Alice. I'm going to talk about physics done by Atlas collaboration, and Atlas collaboration itself is a big collaboration. There are around 3,000 people at the moment from 130 institutions. And in the Nordic countries, so another similar experiment which does the same physics as Atlas at CERN is called CMS, but so it happened that most of the Nordic countries participate in Atlas. So essentially every country except of Finland is in CMS, but Norway, Denmark and Sweden, and this is one of the major activities in high energy physics. In Norway there are around 60 participants, and I was trying to list names here in Bergen. So the 60 participants are in both Bergen and in Oslo, more or less equal weights. And I was trying to list some names here. This is a snapshot in time, relatively recent. There are some people who left recently here, but we have 4 faculty and some number of postdoc researcher, the BSF researcher Heidi Sandaker, and some number of 2 postdocs and a number of PhD students, which you will meet, hopefully, when you come to study with us. And there is a picture picture of faces which you can try to find among the audience if you have time after. Okay, so why we are doing the physics we are doing, and one of the answer is that we are trying to understand the first moment of the life of the universe. So at the beginning, universe, just after Big Bang, was in hot, dense state, meaning that the energy per elementary particle was very high. So high that such high energies per elementary particle doesn't exist anymore or are very hard to find. So we are trying to recreate on a small scale first moments after the Big Bang. So why is it so important? Apparently what happened there determines to a large extent what happened later. Determines the particle content of the universe, how galaxy clustered, how the stars and planetary system evolved, and determines also what elements were available to build us at the moment. So we have a number of messages from this early universe, and one of them, which I'm not going to speak about, is cosmic microwave background radiation, which was frozen into its present observable state some 300,000 years after the Big Bang, so relatively early, given that the scale is 14 billion years. So this is, for example, message which can be picked up by gamma detectors in the space. But this is what I'm not going to talk about at the moment, but just to tell you that the scale here is 14 billion years, 10 to the 28 centimeters. So from the Big Bang to now, the scale developed to 10 to the 28. So these are the largest scales we can talk about. Okay. Petra? Virka den? Snakker litt og enda mer.
Høres det bra ut?
Ja, ok. Ja. Right, so with the Big Bang, we can speak about physics at the scale of 10 to the minus, very small scales, 10 to the minus 28 centimeters. Then the universe is around 10 to the 28 centimeters right now. The physics and what we understand depends very much on the scale we look at. So all humans, including Per Osland, are around 1 meter high. So when we end, this is our usual resolution. 170. Okay. Fine. Zero order approximation. So this is the scale of usual observation. Right, with visible light, we can observe scales from a fraction of millimeters to actually what happens in the universe on the large distances. So we, for example, can observe the clustering of dark matter in the universe with telescopes. Wow.
Hello, hello.
Well, I hope I will not eat the microphone. Well, one of the accidents which might happen is, it has to be very, very close. All right. So, for example, there are telescopes in space. So one of them is Wilkinson Microwave Laboratory, Hubble telescope, which observe microwave radiation, observe radiation from stars and galaxies, which tells us interesting information about matter in the universe. And for example, they tell us that most of matter in the universe is not visible. But then, on the other hand, there is LHC, which you can think of as a super microscope. So this LHC accelerates particles to such energies that we can probe scales of the order of 10 to minus 16 centimeters. So there is a relation which is coming from quantum mechanics, uncertainty of space times uncertainty of momentum, which is somewhat related to energy, meaning that if you want to probe, which has to be a constant. So meaning that if you want to probe something very small, you need to use high energies. And this is the idea behind, for example, electron microscope. So you use electrons in order to have higher energies, shorter wavelength than visible light, so to probe smaller things. And for example, in this institute I'm coming from, there is another microscope developed, matter microscope, which uses neutral helium atoms, due to the fact that there they have higher energy because of their mass, and then they can have even shorter wavelengths. So you can observe really small things. But what we do now is we accelerate particles and protons to very high energies to be able to probe this small lengths of 10 to the minus 16 centimeters and study physics very shortly after the Big Bang. So what is our present picture of elementary particles which we have seen with the previous accelerator? And this is so-called standard model. The name is not so good, and it was invented when there were many models on the market, and one of them was standard than other, and now we are stuck with this name for many, many years, because apparently this model appeared to be verified by data with a very high accuracy. So this model tells us that there exist three families of quarks and leptons, and these are so-called fermions, particles with spin 1/2. And due to the Pauli principle, you cannot put them on, into one bucket and squeeze. So actually there are like Lego blocks. You have to stack them on one another, and that's why they can build matter, they can build atoms and nuclei. But what we need for ourselves to build all the matter on Earth, including ourselves, is just two quarks, so-called up and down, and an electron, and we also have this neutrino flying around. So why do the other families of quarks and leptons, which are heavier, exist? We have no idea, but they were existing shortly after Big Bang. Now they decay, but we can recreate them in accelerators and study, and that's what we were doing for many years. So except of this building block of matter, there are forces, and without these forces matter would not exist, everything would fly apart from each other. So the most well-known force is electromagnetism, which manifests itself as photons, like particles, waves. And you know all about it, but the very important force is strong force. You can wonder why protons, which are all positive charge, so they repel each other, why you can stack them in the nuclei and they don't fly away. This is because of strong force, which is like a glue, and it's gluing this all together. And it's also gluing quarks inside protons and neutrons. So the particles which transmit this force, bosons of forces, which are the field of a strong force, are called gluons. There is also another force, weak force, and in the everyday condition it's indeed very weak. No matter, it's important. It, for example, causes beta decay. It causes reactions which happen in the stars. And we are all children of stars. So if not, right, because we are actually made, all of us, of byproducts as a cycle of star revolution, which leads, for example, to supernovas. So the stars transmutate materials from the lighter to the heavier, and this is happening thanks to weak interactions as well. So at the beginning there was hydrogen, then there was helium, then there are lithium, heavier and heavier substances, and this all led to us thanks to stars and weak forces, among others. Now, in all of that, there was a missing brick, namely Higgs boson. So, importance of Higgs boson is the following. It actually makes electromagnetism different, what we observe, different from weak force. Otherwise, it would be all the same. It makes all these quarks heavier than zero mass. It makes electron different from neutrino. So actually it's very important for the matter as we know it. It gives mass to these elementary particles, and without this mass, atoms would not exist. So what is Higgs mechanism? We think, so there is some cartoon which was shown many times, and this cartoon won a competition of how to explain Higgs mechanism without, let's say, talking about physics. But before I explain this cartoon, I will say that Higgs essentially is a field in the vacuum, so everywhere, to which particles kind of glue itself, and that's why they get a mass, they get an inertia. So this is, let's think of this field as a bunch of people in the room, and now there is a famous physicist, for example, you may recognize Einstein simplified here. Einstein entering the room, and then obviously people will cluster around him. So Einstein becomes very heavy, and he gets a mass. So this is, for example, top quark, the heaviest quark that we know about, which is nearly as heavy as uranium nuclei. But now, except of this Higgs field, actually, to confirm that this Higgs field exists, we need a Higgs particle, which is a manifestation in a particle form of this Higgs field. It's a somewhat similar way in which photon is a manifestation of electromagnetic field. So how this Higgs particle can be pictured? Now there is someone saying, wow, the Einstein is gonna show up, spreading a rumor. And then someone starts to think, oh, maybe the Einstein is already there, and two people cluster, and other people get clustered around. So this is Higgs particle. So suddenly there is a cluster which has a mass which tries to move through the room. So this is the manifestation of Higgs field, Higgs particle itself. And that's what we were trying to discover for many years, and that's what I'm going to talk about a bit later. But assuming that we discovered Higgs particle, is it all just finished, the end of particle physics? Fortunately or unfortunately, not. So there is much more in the universe, even with Higgs discovered, that we can infer from present-day particle physics, from present-day standard model. So for example, if there were only visible matter